All right, so now that we have reviewed the basics of vectors, we want to make sure that we can do application problems with vectors. So the applications of vectors typically happen in physics and engineering problems. One example is using force. A vector can be used to represent force because force has a magnitude and a direction. So typically with force you would say how many pounds of pressure you have or something like that, and then the angle that you're coming at something with. Also, anytime we have moving objects, we can represent their motion as a vector. So we're thinking like a plane with the wind resistance and things like that. So the thing to note about this, and you might want to highlight this, is that in calculus, this is one of the only times that we specifically use degrees. Every other time we've been using radians, but here in this context, we always use degrees. So if two or more forces are acting on an object, then the resultant force on the object is the vector sum of the vector forces. So that means if you have multiple forces acting on the same object, add the vectors together, basically. So add all the forces together. If the sum is 0, the forces are in equilibrium. All right, so for the first example, we are going to look at a tugboat, and they're pushing an ocean liner. I've been a math teacher. So here's the ocean liner. The tugboats are pushing it at these different angles, and these angles are based off of triangles. That's why they didn't write it in the story, because you kind of have to look at the picture to understand how the angles are working. But they set it up so that we have a coordinate axis here, and the ocean liner is being pushed along the positive x-axis. So each tugboat is exerting a force of 400 pounds, and they are pushing it at the angles that were described. So what is the resultant force of the ocean liner? So first thing, we are going to go ahead and write the force for each of the tugboats. So force 1 is going to be the magnitude times cos of the angle, so cos 20 degrees, and then the magnitude times sine 20 degrees. And if you guys recall, that was one of the kind of like formulas that we used. If you were given the magnitude and the direction, you could use that to write your force or write your vector. The second force on the ocean liner is 400 cos negative 20 degrees, 400 sine negative 20 degrees. And so the resultant force is going to be adding the like terms together. So adding the horizontal components together, adding the vertical components together. Now, I know it's annoying to write this out, but these are your notes, so please write it all out so that you know in the future what you did, if you need to look back at it. All right, so I'm going to go ahead and type this in. Now, we are going to work with these numbers that we get here in the future, and we don't want to round in the middle of a problem. So you can see that I rounded when I wrote this down, but as far as using it in the future, I'm going to store this in my calculator. Since this is kind of like the x-coordinate or the horizontal component, I'm going to store this as x because that makes sense to me. So I'm going to hit the store button down here, and then alpha x. And so now anytime I type, there we go, anytime I type the x button, it's going to give me that decimal. And it's only giving me that many decimal places, but it's actually not rounding it. It's using that exact formula that I plugged in to get that decimal. So I'm going to go ahead and put an x in a circle. This is not like a common notation. I have a terrible memory, so that is my own personal notation for how I remember, like, okay, you stored that as x. All right, and then I'm going to go ahead and type in the same thing for the vertical component. That's just 0, so I don't need to store that one. So there's our resultant vector, or our resultant force. So now if we want to describe the resultant force in terms of its direction and its magnitude, for me to find the magnitude, that is going to be 751.754 squared plus 0 squared. And so I'm going to find, actually, since that's 0, that my magnitude is actually just 751.754. So I didn't really need to have that stored in my calculator because it didn't really matter in this case. And then for me to find the direction, I'm going to go ahead and say tan theta is y divided by x, which is 0 divided by that decimal. And again, that decimal doesn't quite matter this time. I'm going to go ahead and use it anyway. So 0 divided by that decimal for x, and tangent inverse of 0. Sorry, I should have explained that work better. I'm solving for the angle, so I need to do tan inverse of each side. And so theta is tan inverse of 0 divided by 751.754, and I end up getting that theta is 0. So for my answer, I'm going to say the resultant force is 751.754 pounds in the direction along the positive x-axis. And I can reference that because the picture had it. If the picture didn't have it, then I might have to use the cardinal directions like north or east or whatever. Okay, so we're going to go ahead and do another story problem like that. So here it says we have a plane traveling 30 degrees west of north at 500 miles per hour. So we're going to run into this sometimes where the problem that we're given does not have an angle that's written in terms of like calculator measurements, but the angle is written in terms of like a compass. And so we have to draw that west of north. You start at north and you go 30 degrees west. That's that angle right there. So on a compass, that's what that would be. As far as what we plug into our calculator, that means that we're actually going to be plugging in 120 degrees. So for the force of the plane, it was 500 miles per hour, so I'm going to say 500 cos 120, 500 sine 120. And then we also have the force of the wind. As the plane reaches a point, a 70 miles per hour wind hits the plane going in the direction 45 degrees north of east. So if I start at east and I go 45 degrees north of that, and lucky for us, that was already in the calculator position. So that's just a 45 degree angle. So the force of the wind is 70 cos 45, 70 sine 45. And so now if we consider both of those things happening at the same time, I'm going to go ahead and draw this picture. So if you can picture the length of this vector is 500, right? Because magnitude and length are the same thing. The length of this vector is only 70. So when you draw it, kind of draw that in comparison. So here's my 500 length going in that angle it was supposed to. And then if I think about, here's an axis, think about that 45 degree angle and 70, maybe about something like that. So we have the force of the plane, we have the force of the wind, so that means that the plane would have actually flown on this path right here because the wind would be pushing the plane a little bit further north than it was trying to fly. So the resultant force is that dotted line vector that I drew. So the resultant force, again, please don't shorthand this, please write it all down because these are your notes. So 500 cos 120 plus 70 cos 45, 500 sine 120 plus 70 sine 45. And we can go ahead and plug that into our calculators. So I get that that's negative 200.503. I'm going to go ahead and store that as x. And then I can go back and take this exact same thing and plug sine in. $482.510. I'm going to store that as y. Okay, so now if I want to find the magnitude of my plane with the wind combined, that's my speed. So I'm going to say that's the square root, and you can write the decimals or you can just write x and y. I'm going to say square root of x squared plus y squared, knowing that I'm using these decimals for that. So square root of x squared plus y squared So the actual speed of the plane is 522.511 miles per hour. So that means the wind is pushing the plane along a little bit faster than it was naturally going on its own. And then for us to find the direction, we're going to say that tan theta is y divided by x. And for me to solve for theta, I'm going to go ahead and do tan inverse of each side. So the direction is tan inverse of y divided by x. And that is negative 67.435 degrees. And so if we look here, negative 67 is actually in quadrant 4. That's on the wrong side of, clearly that's the wrong side because our answer should be in quadrant 2. So if you guys remember, tangent answers repeat themselves on the unit circle every 180 degrees. So tangent of negative 67.435 is actually the same as if I added 180 degrees and put it over here. So since this is in the wrong quadrant, I'm going to add 180 degrees to it. And so the angle is 112.565 degrees. Now we could leave it like this, or we could kind of convert it back and write it in that west of north notation. So I'm going to say, that whole thing is 112.565. If I subtract 90 from that, then I can see that this little piece right here is 22.565. And so I can say the resultant speed of the plane is 522.511 miles per hour, and its direction is 22.565 degrees west of north. So I could say that angle two ways. I could say that it makes a 112.565 degree angle with the positive x-axis, or I could convert it back into the notation of the original problem and say that it's 22.565 west of north. Now, this is truly a pre-calculus concept. In pre-calculus, we would definitely convert it back and have this be our answer. In calculus, these problems are maybe not as common. I'm probably not expecting to see this on your AP exam, but it doesn't mean it's not good to review and make sure that we kind of understand how this is working. All right, so in surveying and navigation, a bearing is a direction that measures the acute angle that a path or line of sight makes with a fixed north-south line. So up here where we said west of north, that's a bearing in this situation. And so the way that you might write that is you might say north 30 degrees west. So that's saying you're starting at north and then going 30 degrees west of that. Or the way they kind of phrased it in a sentence, so that even if you weren't familiar with the notation, you could still do the problem. So the way they said 30 degrees west of north, that's that type of bearing. In air navigation, bearings are measured in degrees clockwise from north. So it might just say something like bearing 300 degrees. So this does not have to be an acute angle. And then you would say you start at north and you would go around. There's 270, 300 would be a little bit more. And then you would say that's a 300, that's a bearing 300 degree angle. So there's two different ways they reference angles in kind of like real life, because in real life, we start at north or we start at south. We use those cardinal directions. We don't usually do our angles in terms of the positive x-axis because that would be weird.